apatite. And yes, it is only spelled with one P. I made that mistake once during a presentation. Luckily, it was a practice presentation for the group of people that I worked with, but in grad school. So it was just kind of a nice little room where we all chuckled at each other. But I will never forget now that this is now spelled with one P forever. Again, the chemical formula is a calcium phosphate. It is grouped in the phosphates. And this particular, well, one of my samples is from Madagascar, the bluish tinted ones. There's another piece up there that's from Morocco. The other ones are from a variety of other locales, but I'll tell you guys the list of locations that are really, really good to get decent samples of this. There really isn't any cleavage on this sample. And I mean, even when I saw my poor apatite sample crash to the floor and shatter, it was just kind of a uneven surface. I think that it can fracture conchoidally in some cases, but mine didn't really show any signs of that. It just broke into pieces. As we discussed, the hardness is 5. That's on the most hardness scale from 1 to 10. So it's kind of in the middle. But despite that, its tenacity is brittle again. So even though the hardness is kind of moderate, it's still very brittle. So it's not going to deform under stress very well. It's just going to shatter. The streak, if you were to streak this on a streak plate, and I'll show you that, it would just show a white streak. Again, you can powder a mineral to determine its streak if you don't have a plate, if you're willing to destroy it or have a copious amounts of said mineral. But I personally just like to use a streak plate. You can get white and black ones. So you can see that white streak there. I wanted to use the black streak plate. Otherwise, if I use a white one, it just, well, obviously you can't see white on white very well now, can you? Now let's look at another sample. Let's say, well, what about the one that's kind of a yellow brown? Is it going to do the same streak? What do you know? It does. They're different colors too. I'm not going to scratch these ones because these are really, really gem quality samples, and I plan on giving one away. Let's see about this one, the one that I broke. Yep, it's all white streak. So another takeaway from this: color is a terrible property to identify a mineral. I talk about this all the time because it's exceptionally important. Quartz can be all sorts of colors, and it's the most common mineral on the crust of our Earth. So it's important to understand that although it's important to list the color, because minerals can be multiple colors, maybe not the best idea to identify the mineral off of color alone. Maybe use it as one of the last identifying characteristics. That's what I would suggest. Is indistinct cleavage worse than poor cleavage? I mean, it just depends on the book and who they're, in my opinion, they're honestly, in my opinion, the roughly the same, but a very, 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 very well-trained mineralogist might tell you differently. They might, at that level, when they're actually writing papers on these things and use those qualifiers for things, maybe that then becomes extremely important, but I don't really. For the scope of what we're doing here, I don't think it's really that important. They're not that different as far as I know. Oh, whether indistinct cleavage versus poor cleavage is the same. I would personally, but I haven't actually looked up the proper list of cleavage qualifiers for minerals. I've never thought to do it. I've never had to. Let's look it up. I don't know if there's any quantifiable way to determine the poor versus excellent cleavage. I don't know how. I'm sure maybe they've mathematically determined that, but I've never studied that part of geology. It does and can have a vitreous luster, which you can see, and that just has to do with, well, how does the light absorb, transmit, or reflect off the mineral? And you can see as I rotate this that the light is obviously reflecting to some extent, but there is still some light that's absorbed, obviously. Now these ones, of course, are exceptionally vitreous, and it can vary, and that actually changes with the index of refraction, which for this mineral I believe is around 1.6. Now, a mineral is considered adamantine, which is essentially really shiny, when it's at an index of refraction of 2. We obtain the index of refraction by dividing the speed of light in a vacuum by the speed of light through whatever medium or mineral we're looking at. And I really like talking about that because I personally like having the quantifiable way to determine things. It's more logical to me, and I like it. But you can't always see that. You can't see index of refraction with your eyeballs. You have to measure it, and I don't have the tools to do that. But nonetheless, it's interesting to me. So, in other words, a vitreous mineral will be 1.5 to 2 in the index of refraction, and this one lands at, I believe, 1.63. That's right, 1.63 to 1.64. It doesn't really vary very much. So it's typically going to be vitreous or lower depending on how weathered that mineral is, but it's typically just vitreous. The diaphaneity also has to do with is the mineral see-through or not. In this case, it's translucent to transparent. Typically, it's not opaque. Habit can be tabular, prismatic, massive, granular. Oftentimes, these minerals actually occur as prismatic, so you can see well-defined crystals. Some of the best minerals that you see in this way are actually in pegmatites, which we talk about a lot because pegmatites are your really big crystals. Those are injections of magma that have had time to cool very, very slowly. So you have these big crystals. Typically, they're somewhat granitic. So you've got your feldspars and your quartz, as well as whatever else you can have beryl, which is your emerald and aquamarines and things, which I have a sample of actually. This is my favorite pegmatite. You can see a big chunk of beryl in there, which is one of the prized minerals for gemology and just collectors worldwide. It's a really, really cool mineral. This one doesn't have the best colors, but there are a couple areas where you can see a little bit of apple green. And I'll try to show that to you in the microscope camera. But this is the pegmatite. So you can see how very large those individual minerals are. Oh, all of the different types of apatite, because there are three different end members. Some of which are more common than others, but they are all identical in shape. The shape that they take is hexagonal. You can see that really clearly on this one here. Oops, if I could pick it up. You can see the six-sided shape really, really well on both ends of this little mineral. You can't see it on this guy here. This would be considered massive. It doesn't really take any shape at all. But this one does. This one actually does too, but it's broken, sadly. Let's see if you can see some of the six-sided. I don't know if you can see it anymore. Oh, you can kind of see it there. You can kind of see it, the hexagonal shape there. You see all those little tiny pieces that broke? It's actually pretty easy to put them back together like a little puzzle, and I want to glue it back together. I want to find something that's not going to be obvious that it was adhered back together. I feel sad. Like, maybe I should keep it that way so that I could use it for learning purposes. Like, hey, look, this is an example of how the cleavage is, poor. Anyway, but all three of the end members actually differ in composition, again, because they can either have amount of fluorine, phosphorus, or hydroxyl. I'm sorry, fluorine, chlorine, or hydroxyl. The chlorapatite, the chlorine variety, is relatively rare. The carbonate fluorapatite occurs in fossils, bones, and teeth. So by that I mean this is actually one of the secondary forms of this mineral. You can get the replacement of your bones and teeth by apatite. Our bones and teeth are actually made of this. It's just not it's a different type of apatite, and it later can become the mineral apatite through mineralization and burial, like we talked about earlier, during processes of lithification when you get the formation of sedimentary rocks. Oh, the name of it actually means deceit in Greek for apate, I think, because it looks like so many other minerals. Again, because of the color, I think it used to easily look like others, and because it's a hexagonal shape. One of the minerals it used to be confused for was your aquamarines and emeralds. Again, that's beryl. It's also hexagonally shaped. Although apatite is harder, I don't know how many properties they knew about these minerals when these things were discovered. So they were probably easily confused for one another. Oh, olivine is another that it was confused for. Olivine was one. Varieties of beryl were another. Amethyst was another one. Amethyst has got a six-sided shape and can be in multiple colors. It's a variety of SiO2 quartz. No, they do not only occur in Madagascar. The thing is that the first sample that I got of apatite was from Madagascar, so that was the locale of the specific sample that I have. But I also have a sample from Morocco, and this one is from Quebec, Canada. I don't remember. Honey, do you remember where the two little yellow ones were from? The little yellow guys? I've got a list of places that you can find these. Yep, apatite is commonly used as a cheap replacement for emeralds in aquamarine. It used to be confused for it, which is why it was the name Deceit. Or maybe they purposefully sold it for those, which is why they named it Deceit. I don't know. Olivine is cheap. It's the first mineral to actually form, first major mineral to form in bodies of magma, and the last mineral to form, well, within temperature ranges. So you get the first mineral to crystallize in a body of magma is olivine. The last is quartz. Oh, these ones are from Mexico. Yeah, Mexico is one of the areas that you can find really decent samples of apatite. We talked about it being hexagonal. We talked about it being in the phosphates. It can occur in igneous and more metamorphics. The metamorphics that it actually occurs in occasionally are hornfels. I've yet to find one like this, but I'm curious to see what they look like. But igneous, again, would be the pegmatites, like the one that I showed you. Of course, the uses would be fertilizer because there's fluorine in the fluorapatite variety. Oh, and phosphate, of course. Phosphorus is useful. The thing with the phase diagrams, I could pull one up. In fact, I should actually add one to my lecture for this. I love phase diagrams. Phase diagrams are great. They give a visual to describe just how these things work. When I say, oh yeah, they're a solid solution series, it's like people are like, what? And of course they would. I don't expect people to know what a solid solution series is. It's just a weird geologic thing that happens in chemistry. It's just that these minerals can actually occur with differing amounts of fluorine, chlorine, and hydroxyl. They just, depending on the system that they form in, can have varying amounts. The calcium and the phosphate is always there. But the fluorine, the chlorine, and the hydroxyl in this chemical formula are always switching places. And some of them are more common than others. The fluorapatite is probably, I think, the most common. No, but this isn't what we want, because there's the phosphate, there's apatite at the top, right? But there's calcite. And I don't know what the sodium carbonate is. But yeah, this isn't a phase diagram for apatite. This is a lot more complex, which is fine. It's just not going to do the lecture justice. So this has the fluorapatite. And this is a silicate, and this is a silicate. This is albite, or some variation of albite. Oh, no. Fluorapatite is actually the name of the variety with fluorine in it. It's the most common phosphate on Earth. Secondary apatite forms from bones and teeth. Oh, this is one thing I didn't know before today. Bedded marine deposits are frequently mined as a source of phosphorus because of apatite. And it makes sense, because if you get a lot of marine organisms with bones, you then get, secondary apatite forming, which has phosphorus in it. If it's apatite, it has phosphorus. It's a phosphate. So that was something interesting I didn't know about. I had no idea. Places that are really good for finding gem quality samples or massive, just a lot of samples in general are U.S., Mexico, Namibia, Russia, and I think I wanted to say Morocco, or I think it was Morocco. But those four I know, U.S., Mexico, Namibia, and Russia, all have really, really notable deposits. Yeah, Arkansas does, Watcher of You. There's a lot of really good deposits all throughout the Appalachians, essentially. The weathering of the mountains has exposed a lot. I can get the bot up and running. So this is one of the sides of the blue pieces that is actually really strange looking. Like, you can see one of them here. Let me do that. That might help a little bit with some of the color. Sorry, this desk is kind of cheap and it shakes a bit, but you can see the top of that. It's very, very vitreous. You can see actually some of that conchoidally, some of that conchoidal fracture on the. And you can go even further into the zoomage, which just doesn't really show a lot. Let's see the side. Maybe that looks nicer. Oh, it's actually kind of hard. It just looks pretty glassy. Blue. You don't see any of the hexagonal shape on this one. It's pretty massive. Or thick tabular. Oh, there's a nice little blue chunk there. There's some really nice, oh, right there. There. Oh, that's pretty. That's a really, really pretty blue. And that apatite. Quite nice, actually. It's really nice. No, this is actually a phosphate. We're not even in the silicates. I don't remember the last silicate we went over, but this is the phosphates. And we just went over all of the science of the phosphate. In fact, Mia is from Madagascar. No, Morocco. Morocco, blue Madagascar. This one was Morocco, blue Madagascar. Got it? I confused myself. I apologize. So this one is, I think, a bit more vitreous than the blue sample, and I just think it's because the planes are just much more evident and easily discernible. But this is one of the planes. I'm trying to see if I can get that reflectant. That's all right. There's some decent striations on this sample too. It's a bit translucent. I mean translucent. Yeah, it's not transparent. You can see inclusions inside the mineral. That actually might be superficial. I'm not sure what that is. But oftentimes, as we know, inclusions can change colors of mineral. Ooh, that's pretty. That's really nice. That's really nice. Sometimes you get to see these tiny little bits in the microscope camera that you miss. And you miss in hand sample. You just can't see with the naked eye. It's really, really interesting and pretty. So this guy right here, that little guy right there, about as big as my fingernail. But this is how clear that apatite is. You can see straight through to the dusk on the other side. I'm gonna put it on a white piece of paper. See how clear that is? It's exceptionally clear. Now it's just on a white piece of paper. You can't see any detail really because it's just so... There's a little bit of there's a surface on here that's curved, giving it a bit of a nice... Let's see if I can find it. No. Oh, yeah, I like this end because you can see... You can kind of see how a little bit of that conchoidal fracture, which is nice, but it's nearly doubly terminated, which means it's got two nice ends. This end is pretty good. You can see a little bit of that there, but I'm trying to find that side that gives that nice little rainbow sheen. Hold on. I found it, I think. No! It rolled. Right there. Oh, that's got some inclusions in it. Oh, that's cool. When you hold this up to the light, though, there's this area, I think it's this area here, that actually looks somewhat iridescent because of the way the fractures are. Oh, yeah, I found it. It's right here. Oh, my God, it's so cool. I found it. I wonder if I can show it to you in the camera. I really, really want to show you. Please work. Is that it? I think. There it is. You can see a bit of it in this camera here. Look at that. You see that? It's just, oh God, it's so cool. I really like this one. The only reason I'm giving this one away and not the other is because there's a tiny piece of magnetite on the other one, and I think it's cool. But that other one isn't, the one that I'm keeping isn't really, I don't think it's gem quality because the magnetite on it. It's for others, they probably wouldn't use it for gems and whatnot, but I would. I love this piece so much. And I'll show you the other one. I'll show you the little piece of magnetite on it, and it's got a lot more fracturing as well on the end here. So there's one of the, I think that's the magnetite on it. I'm trying to find some of it. You can see some oxidation though. So it's pretty cool. But you can see there's a lot more pits on the surface. It's not nearly as smooth as the other one, But there's a little bit of that iridescence on the end here because there's a bunch of fracturing. A bunch of that conchoidal fracturing. So you can see a little bit of it, which is really, really neat. But there's all sorts of stuff on this one. But that right there is the reason I'm keeping it, because it's just so cool. If I can get the angle right, you can see the shape of it. Come on. There. You see that little pyramid on there? You see that little pyramid on there?